In this example, we're told we have a system consisting of a copper tank with a given mass. So let's write out the mass of the copper. That's 13 kilograms. And inside that copper tank, there's some water that has a mass of 4 kilograms. And there's an electrical resistor here of negligible mass. The system's insulated on its outer surface, so that's this dark black line on the outer surface there. It means there's no heat transfer through that outer surface. Initially, the temperature of the copper is 27 degrees C and the temperature of the water is 50 degrees C. So let's write that down. The temperature initially of the copper is 27 degrees C. The temperature initially of the water is 50 degrees C. The electrical resistor transfers 100 kilojoules of energy to the system. Our system here will consist of the copper and the water. So I'm going to draw a dashed line just on the inside of the insulation to indicate that both the copper and the water are both part of my system. And so the resistor is bringing in some electrical work that's being done on the system. So let's write that down. The electrical work on the system is 100 kilojoules. So that's electrical work that the electrical resistor brings in. Eventually the system comes into equilibrium. So when it comes into equilibrium, what will happen is the copper and the water will have the same temperature. So T2 copper will equal to T2 of the water, so I'll just call it T2, just the final temperature. Now another thing that I'm going to do in the analysis here is I'm going to assume that the water and the copper are both incompressible substances. So I'm going to assume copper and water are incompressible. That's a pretty good assumption for solids as well as liquids. And you'll see that that'll play into this in a little bit. So I'm asked to find what the final temperature is of this system. When I think about this, this is a first law kind of an analysis, because what's happening is initially the system has some internal energy because we have some initial temperature. So we have some internal energy here, and then we're going to do some work on our system that'll change the internal energy of our system. So that is really a first law analysis. So let's write down the first law for that system. So the change in total energy of the system is equal to the heat put into it plus the work done on it. Notice that I wrote the first law with the plus work done on because I know that there's work coming into it from the resistor, so I'm using the plus on convention. Now the heat transfer is 0 because we know that the copper tank is well insulated, right? It says the system is insulated on its outer surface, so we don't have any heat transfer. The work on that's 100 kilojoules. The change in total energy of the system will be the change in the internal energy plus the change in the kinetic energy plus the change in the potential energy of the system. But since the system's not moving, the change in kinetic energy is 0. It's not changing elevation, so the change in potential energy is 0. So in the end, we have the change in the internal energy is equal to the work done on that system. Now the change in the internal energy will just be the final internal energy minus the initial internal energy. So in order to determine what this change in internal energy is, this is where I'm going to make use of our incompressible substance assumption. We know that for an incompressible substance, the change in the specific internal energy is just C times the change in temperature. Actually, more generally, it looks like this. It's the integral of C times dt as we go from our initial to final temperature, because in general, the specific heat is a function of temperature, but we're going to assume that it's incompressible and the C is about equal to a constant. Now the reason I'm assuming that the specific heat is about a constant is because when I look at the temperatures here, we're at 27 degrees C, 50 degrees C, 100 kilojoules. I'm going to assume that the change in the final temperature, T2, that we're trying to find, I'm going to assume is pretty close to these values. And if the temperature is pretty close, that means that our specific heat's not going to change a whole lot. So it's pretty reasonable to assume that it's a constant. So I'm going to make that assumption. I'll come back and just double check it at the end. So if I assume that the specific heat's a constant, I can use this form to find the change in the specific internal energy and relate it to the change in the temperature. So when I write out the U2 minus U1, what that's going to consist of is I'll have the mass of the copper times the specific heat of the copper times the final temperature of the copper minus its initial temperature. And then I also have the mass of the water times the specific heat of the water times the change in its temperature. Okay, so this is the change in internal energy for the copper, and this is the change in the internal energy for the water. So that gives me the total change in internal energy. Okay, in fact, you know what? Let me make that more explicit. Let me write it this way. So this is equal to that, which is just the change in the internal energy of the copper plus the change in the internal energy of the water. Okay, so that's the way I've written it down. And just remember, T2 is the same for both the copper and the water. All right, so we know some of this information. We know the mass of the copper and the mass of the water. That was given in the problem statement. We know the initial temperature of the copper and water. So that was given as well. We're trying to solve for the final temperature, T2. So one of the things I need to know is what the specific heats are for the copper and the water. So to find those, I can refer to a table. And I've posted a table here. This comes from the Moran et al. Textbook. And what it is it's the specific heats for solids and liquids. They give it as C sub P, but remember, for an incompressible substance, C sub P and C sub V are the same. I often just call it C. So they just put C sub P here instead. So it's the specific heats for various substances. So we're dealing with copper. So that specific heat is right here, 0.385 kilojoules per kilogram Kelvin. And then we're dealing with water. You'll see down here that water, the specific heat depends on what the temperature of the water is. So since we're pretty close, I think our initial temperature for the water was 27 degrees C. That comes out to be 300 Kelvin. Oops, I'm sorry, I have the wrong one. The initial temperature of the water is 50 degrees C. So that temperature is about 323 Kelvin. So that's my starting temperature. Now granted, the temperature does change throughout the process, but it'll be pretty close, I suspect, to about 300 Kelvin. So let's go back down here. So when I am choosing the value for water, which value to use, let me just go ahead and use, I'm going to use the 300K value. And the reason for that, so let me just circle it or box it in. And the reason for that is I know that the initial temperature of the water is closer to 325, but I suspect since the copper temperature is 27 degrees Celsius, which is 300 Kelvin, that our final temperature is going to be somewhere between these two values. So I'm just going to choose the 300 one. Really, I'd probably be better off, a little bit more accurate, if I use the average of these two, because the final temperature is likely to be between these two values, or pretty close to them. So I'm just going to choose that lower one. If you chose this 4.182, that's totally fine. It may actually be a little bit more accurate than what I'm doing, but either one is fine. They're both pretty close. Okay, so let me write those down. So from a table, the specific heat for copper was 0.385 kilojoules per kilogram Kelvin. And the specific heat for water, the one that I chose, was 4.179 kilojoules per kilogram Kelvin. Again, you might choose a slightly different value than I used here, and it would be fine as long as it's close. All right, so now I can solve for the final temperature. Remember, we know the value of the work done on the system. That was the 100 kilojoules of electrical work. We know everything in here except T2, so we can solve that equation for T2. I won't go through the math for that, but if you do solve it, it'll come out to be 322 Kelvin, which is about 49.3 degrees C. That's what it comes out to be in the end. One thing I just want to highlight is I can use degrees Celsius here in the temperatures. I don't have to convert them to Kelvin. It's fine if you convert them to Kelvin, but you don't have to. And the reason is because these are differences in temperature. So a 10 degree difference, a 10 degree Celsius difference is the same as a 10 Kelvin difference, right? They're the same size, since I'm dealing with differences here, I can just use degrees Celsius rather than Kelvin. But it's fine if you want to use Kelvin instead. That works too. And when you multiply it by the specific heat, there's a Kelvin in the denominator here of the units. Again, it's the specific heat multiplied by a temperature difference. So again, it's the temperature difference can either be in degrees Celsius or Kelvin. It doesn't matter. They're the same magnitude. Now, looking at this, I ended up with 322 Kelvin, started off with 323 Kelvin. So I might have been better off when I chose my specific heat to end up using this one here for 325, the 4.182. That would have probably given me a more accurate result, but that's fine. We're still pretty close. Okay, so that's really it for this problem. Just to recap, we recognize that this was a first law analysis problem because we were looking at changes in the internal energy which are related to temperature. So we wrote down the first law, making use of the fact that it's well insulated, and we're given the electrical work. The change in the internal energy, we made use of the fact that we're dealing with an incompressible substance and assume that the specific heat didn't change with temperature by very much. So we could write this expression. Finding the specific heats, we just used a table to find those values. And then the rest was just some numerics to end up with our final temperature. So we'll end it there.